just a capacitor. Want to see the input signals and output signals properties in the oscilloscope of a capacitor. So I'm connecting the input signal this side of this capacitor, and I'll take the output signal from this side of this capacitor. I have here 2.2 microfarad capacitor. I have just connected as I have seen in the board. So that's the oscilloscope's one probe just here. So this is channel 2, and the blue wire is oscilloscope another probe, which is channel 1. So I'm going to see the input signal from this channel 1 and the output signal of the capacitor wanna see from channel 2. So, and this clip is from the signal generator. So let's see what's happening for square wave first. Currently there is no signal and the capacitor is completely discharged. And then when I turn on this channel 2, and what's happening, you can just hold this for now, and from the screen you can see the capacitor doesn't want to pass the DC. It just charged up and then it slowly tried to discharge and completely discharging. And then when the negative pulse of the square wave, it just charged up negatively and then slowly just come back to 0. It doesn't want to pass the DC completely. It's just the nature of a capacitor. So if I just increase the frequency every time, it just charged up and then it doesn't want to hold the DC completely. It just following the DC only. What will be happening if I just connect this output line to the ground? So I'm just connecting this to the ground and see the output is just now 0. Now I'm replacing the ground line with just a simple diode. For the positive pulse, it's just completely doing like before, and for the negative pulse, as soon as the negative pulse is happening, the diode is on, because I have just connected the diode like this. This is the cathode and this is the anode. So when the negative pulse is coming in the input, as soon as the negative pulse is coming in the input, the diode starts getting on. So it's just acting as a short circuit here. That's the thing happening. As soon as the negative pulse is happening, the diode is on, and that is why it just acts as a short circuit, as I shown you before, like when I connected only to the ground. It's just acting as a ground connection. Now I'm going to change the signal type from square to sine wave. Let's see what is happening. So I'm changing this one from square to sine. You can see as soon as I just change, there is 0 voltage for the negative signal. For the negative peak, there is 0 voltage. The voltage will be 0 for the negative peak, but for the positive input peak, the diode is just off, and then the circuit is like a open circuit, and then the output also from the capacitor is just following the input. And that's the completely inverse properties of the previous one. So I'm changing it back to the previous position. So put it back again, and you see. So let's see what is happening if I increase the frequency from the signal generator. So there is no signal now. I'm increasing the signals. For the positive peak, the output is just following the input one, the yellow. For the negative peak of the input signal, it just acts as the output acts as a ground. So it doesn't want to follow the negative peak, because the diode makes a short circuit connection from the ground to the capacitor's output. But why the output signal is just raised up a little bit up, than the input signal, because when the capacitor is just charged up, when the diode is connected to the short, to the ground, the capacitor starts charging up, and then it just staying at the 0 voltage. As soon as the voltage is just rising up from there, and it also starts rising up from there. So the input signal starts rising up from the negative peak to the positive peak, but the output signal from the capacitor, it just starts rising up the voltage from 0 voltage to the positive peak. So that is why the difference between the input signal and then the output signal. Let's see, if I increase the frequency more for 50 Hz, you see there is a very big difference. There's a very big difference. The peak signals, the output peak is now 5.2 volt, but for the input peak 2.72 volt. So what do you call this circuit? So this circuit is called a clamp circuit, because it's just clamped up from the negative side to the positive side. It doesn't want to go to the negative side. It just always stay in the positive side from the 0 line. So that is why it just clamped up, and it's called a clamp circuit. Now I'm going to change the capacitor and the diode. The output signal is just like this. You can see the output signal is just staying only on the positive peak of the input signal. The output signal is just on the peak. It just taking only the peak. That's why this circuit is called as a peak detector. If I increase the frequency 30, 40, 50, and then stop this one and see, it's just a completely nice DC. So I have talked about the clamp circuit and then the peak detector. The clamp circuit was like this. So the first circuit was this capacitor and then the diode, and then the second circuit is just the diode and the capacitor, and this is the combined circuit. So I'm gonna take the output P out from here, and that's our input B in. So here is my combination of these two circuits, the clamp circuit plus peak detector. So I have connected all these components as in this circuit diagram. So I'm going to take the output from here, the peak detector circuit, and this circuit is the clamp circuit. So capacitor and diode, these two makes the clamp circuit, and then this diode and this capacitor makes the peak detector. So you see the clamp circuit output plus peak detector. I don't have one more channel to show you the input signal at the same time, because my oscilloscope has only two probes, two like input probes. So that is why I can't show all this together. So I'm just increasing the frequency now. Increasing the frequency, you can see, like as soon as I increasing the frequency, there is like it just makes like a DC line. You see, it just completely DC. This is the clamped output, and this is the peak detector output, but the input is down there. I'm showing the input as well now, changing the probe to the input. You can see the input is there, input is down there. So what we can get, finally from this AC input, we can get like a clearly DC output. If there is a little bit like ripple on the top, if I increase the frequency more, so we can get rid of the ripple as well. Like I have set this up now 50, you see, for 50, there is no ripple, just a complete DC line. So what we can get from these two circuit, the combination of this peak detector plus clamp circuit, we can achieve the complete output multiplied RMS values, multiplied to and then convert it to DC. So for a small AC signal, we can like make a multiplier, voltage multiplier, and convert it to DC with this circuit. That's why this circuit is called voltage multiplier. So we can add multi-stage, like we can make like voltage tripler and quadrupler, and like we can 4 stage, 5 stage, 6 stage, as long as you want to. We can add this stage to the, like always the peak detector at the last stage, and the clamp circuit one after one. You can like put a lot of stages and then multiply the voltage.